All right, hello calculus. Today we are looking at graphing derivatives and antiderivatives and really just being flexible between first derivatives and taking a derivative of that, or antiderivatives, which means going in reverse. So if I give you the derivative, can you draw the graph that it came from? So really interesting. We want to be able to go forwards and backwards. And it's interesting that we're talking about this now. This is what we'll be looking at second semester, antiderivatives. So now that we know how to take a derivative, we want to be able to go in reverse as well. You have a Delta Math assignment. So first, remember, a derivative is really slope and slopes of tangent lines. And so we want to be able to look at a graph and sort of estimate the slope. So here I have a linear function. It has a constant slope. And I can figure out what the slope is at that point by, maybe finding some nice points. Here's another place where it crosses, and that's kind of nice because you can see that we have to go down 2 units and right 3 units. So the slope is negative 2 over 3. Because this is a constant slope, it is not changing, it is linear. Everywhere on this line has the same slope. Well, that makes sense. What's the slope of a vertical line? Undefined. Very good. And we know that we can't take a derivative where we have a tangent line that is undefined. What about the slope at this point? Well, I'm going to get my trusty rusty protractor and hold that up there. Let's see. And so again, we're just trying to approximate this slope. And so, well, clearly the slope is going, that tangent is negative. And, well, let's see, those are relatively the same points. So I would say I would go down 1, down 2, and then over 1, over 2. So here we have what looks to be a slope of about negative 1. Here, holding up my nice little straight edge, right at the bottom of the curve, that's easy to tell. Those are probably the easiest to tell. We have a slope of about 0. And certainly, we're changing from a negative slope to a positive slope. And in order to change, you would have to pass through 0. So pretty safe to assume that that is a slope of 0. And then here, again, on the other side, I can sort of sketch in a line, and it looks like I would have to go, say, up 1, up 2, and then over 1, over 2. So again, this looks like it might be a slope of 1. I would say that probably the most important thing to think about is that this slope is a positive, oh, sorry, not positive, this slope is a negative value. And certainly this slope is a positive value. And those are oftentimes the things we really need to think about. Here we have a slope that is negative, and here we have slopes that are positive on the right. Here, let's see, this first point looks quite steep. Let's see now. Boy, oh boy, very steep here. Very steep line. I don't know what that slope is, but it is a positive value and it is steep. I don't know, maybe it's like a positive 5 or 6 slope. Very steep indeed. What about this slope here? That one. There we go. Drawing that sort of line out. That one, at this point, it looks like got to go down 1, 2, 3, ish, maybe 4 and over 2. So maybe this is a slope of like -2. I don't know. Maybe -3. It's pretty steep. And then, of course, this point right down here, again, looks like a slope of 0. But here is the important part that we were just thinking, hey, these slopes are positive. Here we have slopes that are negative, and I really want to be able to identify slopes that are 0. Those are really helpful. So example 2, we want to match the graph of f with f prime. So the graph of the function and its derivative. So algebraically speaking, if I have a function like x cubed, then if I want to take the derivative, we know how to do that. That's really easy to do. Bring down the 3 and reduce the power by 1. So when I have a function that's a cubic and I take a derivative, I get something quadratic. And I like to keep those things in mind. So what I'm going to do is start with what I think is the easiest function. I'm going to start with this one here, which is a nice little linear function. So it is a line, and we can clearly see that the slope here is 1. We're going up 1 and over 1, up 1 and over 1. So it has a constant slope of 1. Well, guess what? The derivative is 1, which is right here. For this entire line, at every single point on this line, it has a slope equal to 1, which means the derivative is equal to 1. So C matches with graph number 1. All right, let's look at this. Here we have a quadratic function. And again, if you're thinking about the algebra here, you know that this is an x squared function. And if you wanted to take the derivative of it, you drop down the power in front and reduce the exponent by 1. So if we start with a quadratic, then the derivative would be a line. So what's happening here? You can see on this side we have slopes that are negative, which means the first derivative would be less than 0. All of these slopes at these points are downhill, and they're getting smaller. So like this might be a slope of -2, this might be a slope of -1. Right here at 0, we have a slope f prime is equal to 0. All right, so we have negative values for the derivative, then we have a slope of 0. And then over here, like at this point, you can see that our slope f prime is greater than 0. Maybe it's a value of 2. Maybe right here it's a value of 1. I don't know. So what's happening? You can't hardly see that, I think. So that would be f prime is equal to 0. So here our output is 0. At x equals 0, we have an output of 0. To the left, all of our slopes are less than 0. All of our slopes are negative. To the left, all of our slopes are negative values. And you can see that I was thinking that our slope, I guess I would say f prime actually. You could say f prime at -2 approximately looks like it's a slope of -2. So that's what I'm seeing here. At -2, if this is my derivative graph, the slope is -2. Here, at +2, the slope is approximately, it looks to be like +2 to me. And so you can see here, our output is +2. Here, the slope at 0 is 0, approximately. And so that's what's happening. So this A matches with graph 2. Okay. Let's look at this one. And again, so sometimes estimating things can be really, really helpful. So when I look at this second graph here, I'm maybe seeing this point right here, and I'm thinking about, well, this point, what would it be? Let's see, what's the slope at -1, approximately? Well, this slope, if I were to extend it, maybe it'd be like up 1 over 1, maybe, approximately +1. And so when I'm looking at these two graphs, I see that here at -1, it does appear to be an output of 1. And what's happening right at 0? F prime at 0 is approximately 0. It definitely looks like it's 0. So again, the output is 0. And then again, looking here, F prime, the slope at 1, if you're thinking about what is that slope there, it does, well, that's a bad line. Yeah, it's maybe it's approximately 1 as well. And that's definitely the closest. When I look at this one, it's like over 2, about 2. That doesn't seem quite right. So I think this goes with graph 3. Now this one is very interesting. And you can see that we have some very interesting values here. I'm going to start with this one right here. That slope you can see is 0 because it's reaching a maximum there. So F prime, at what value is that? I don't know. It looks to be about -0.5. Has a slope of 0. And you can see here at -0.5, we're at 0. F prime at 0, here we're going downhill. It's negative. Maybe it's -1. And you can see our output is 0, -0, -1. And then here again, the slope at 0.5 is horizontal. It is a slope of 0. And you can see it here. We have an output of 0. So D matches with graph number 4. So I do think it's helpful to sort of just look at your function and approximate the slopes. It's a really good skill. And to know that here you see we have all of these slopes are negative. So that translates to being below the axis. Then we hit 0, and then all these slopes to the right are positive, and that translates to being above the axis on our derivative function. And so again, here we have all these positive slopes are all positive on the derivative above the axis. Here we have negative slopes, which below corresponds to being below the axis. And here we have positive slopes, which corresponds to being above the axis on the derivative. It can be confusing, so take your time with it and really think it through. All right, example 3, use the graph of f to sketch f prime. So we want to sketch a possible derivative. And again, I think the easiest thing to identify are the where we have a slope of 0. So I think the good place to start is find where our slopes equal to 0, where we have horizontal tangents. And so you can see here, right here, we have a horizontal tangent. Well, what does that mean? It means at -2, we have a slope of 0. That's a derivative point. It also means that the derivative at -2 is 0. So at -2, we have a slope of 0. We can also see right here at +2, we also have the derivative is equal to 0. Remember, that's what derivative means. Derivative means the slope. So at f of 2, we also have a slope of 0. Now, to the left of -2, you can see that all of these slopes are positive. All of the slopes are going uphill from left to right. What's happening to those slopes? Well, they're starting steep, higher values, and they're sort of decreasing, aren't they? So they're starting steep, maybe like 2, and then they're getting lower and lower in value. To the right of -2, all of these slopes are negative. And you can see they're all going downhill, but they're increasing a little bit. We're pretty shallow slope here. So maybe like -0.5 and then -1, and then maybe it gets to -2. I don't know. But then it starts to decrease again. So we're back to like -0.5 and getting closer and closer again to 0. So we're going negative or getting a little more negative, but then we are also turning around and going back to zero, getting closer to zero. So we're getting shallow negative slopes, then steeper negative values, then more shallow negative values. And then to the right of positive 2, once again, we hit 0 and we start transitioning again to positive slopes. And they're just getting a little bit higher, and we stop at about 3.5. So they're just getting more increasing values. And so what shape does that look like? It kind of looks like a quadratic function, a parabola. And there you go. So I kind of like how I color-coded that. Positive, getting closer to 0. Then we have negative values that grow but then get closer to 0 again. And then we have increasing slopes to about there. I don't know what the slope is at this point, so I'm not going to include any information. We can't take the slope at a single point. This one's a little trickier. This is a very interesting one. Again, we're thinking about the slope. Well, we clearly have in this section a line. It is a constant slope, and you can see that it's going up 1 and over 1. So this is constant slope of 1 for every value to the left of 0. It's a slope of 1, which means f prime for any value less than 0 equals 1. So all of those slopes are 1. Everything to the left of 0 has a slope of 1. So let me ask you then, what happens right here, which is a very tricky spot? It's very curious. I have no idea. I'm going to skip it for now. So something weird is happening there. But let's look to the right of 0. And when I'm looking at this curve, I'm thinking it kind of looks like a parabola, half of a parabola. And if I ignore this left-hand side, left of 0, then it looks like right at 0. It looks like it's coming in and getting very, very close to a slope of 0. Very, very close. But I'm not sure right exactly. So I don't really know, but I'm guessing, but I'm not going to include it. And that's the trick here at this sort of sharp point. We can't take a derivative there because it is sharp. And you see that when we're coming in from the left, we're constant slope of 1, unchanging, does not change. So the slope is 1 as we approach the limit from the left. The limit from the right, we're approaching 0, a slope of 0. Because those slopes are different values, a value of 1 versus a value of 0, we can't take a derivative. The limit from the left does not agree with the limit from the right. And so it's undefined there for derivatives, that is. And then on this side, you can see that we have positive slopes that are increasing, getting higher and higher and higher. They're starting out very shallow, like 1/2, and then maybe 1, and then I don't know, what does that look like? Maybe that's a slope of 2. That's pretty steep. So I'm guessing that it's sort of this sort of linear shape. If we were thinking this was x squared, then if I took the derivative, it would be like a slope of 2x. So that's sort of my reasoning. But they would give you pretty clear differences. So something like that, if you were thinking it was a slope of 1, that wouldn't quite make sense, would it? Because if this was, well, it might actually. Maybe this was like 1/2 x squared. If I took the derivative of 1/2 x squared, then yeah, that would be x to the first, so 1x to the first. So it could be either one. We're not terribly sure because we're just guessing. We're just trying to sketch it. So not to worry, you won't have very many of these. Okay. This is the important part though, sharp point there. So that was really important that you pay attention. We have a sharp point, you have to be very, very careful. No derivative there because of the sharp turn. Okay, can't take the derivative. All right, I'm going to pause this video and start my second part.